An atomic blast. When matter is transformed into energy by a nuclear fission, something is created which is more than a pyrotechnic display and blast energy common to ordinary explosions. Hiroshima is visible evidence of the tremendous physical energy released by an atomic explosion. But other forms of energy, such as the ionizing radiation given off by the radioactive particles in the atomic cloud, must also be considered. These radioactive particles can be distributed over wide areas by the wind or precipitated by rain with possible harmful effects. Moreover, with certain types of bursts, many substances in the vicinity of the blast can be impregnated with fission products which will emit ionizing radiation in harmful and even deadly amounts over long periods of time. Any atom burst is a breeder of dangerous radiations. But Tess Baker at Bikini proved that the surest spreaders of such contamination are submarine and possibly underground detonations. But whether these radiations are absorbed into the body by contact, by ingestion, or by exposure, ionizing radiation may disrupt the molecular structure of the various and complex substances which constitute a living organism. But how do you identify and measure a menace that cannot be seen, has no taste, no odor, and cannot be heard? This is the question that must be answered if man is to intensify and broaden his use of atomic power. Today, the ability to wage atomic warfare is shared with others. Next time, we may be on the receiving end. If that happens, we can't arbitrarily condemn a center of population as a no man's land because of contamination. It may be vital and strategic in a military sense, a key industrial center. There'll be salvage operations, fires to fight, relief and rescue work. What can be done in a bombed area? What procedures should be followed? These are questions for the command decisions of authorities. Like all momentous decisions, they must be based on facts. There will be no guesswork because of RADIAC instruments. RADIAC, short for radioactivity detection, identification, and computation. These instruments are miracles of sensitivity designed to provide us with a sixth sense. Each has a special use and purpose, but all of them share one thing in common. They measure the ionization produced by radiation. Ionization, the action that occurs in a RADIAC device, is better illustrated than defined. Think of it as a game of atomic pocket billiards. The white balls represent the nucleus of an atom. The black ones, its electrons arranged in orbits like the planets of a solar system around its sun. The cue ball is radiation, which strikes an electron, knocking it away from its atom and thereby producing an ion pair. Another hit, another score. This is the game that goes on inside a pocket dosimeter. It has a dial that what the player is doing. It keeps score. And the pocket of the table represents the instrument's collecting electrode. A pocket dosimeter is basically an electroscope like this, which you'll probably remember from your high school physics. The electroscope with the leaves of its electrodes together is dead, uncharged. By passing a comb through the hair, a static electric charge is picked up and transferred to the electroscope. The metal leaves carrying the same charge repel each other. But the radiation given off by a radium button produces ions which neutralize the charge. The motion of the leaves as they collapse is a measurement of radiation. The movable leaf of the pocket dosimeter is a tiny quartz fiber about 1/10,000th of an inch thick. To prepare a dosimeter for use, a charge is placed on it with a charging box, so that its graduated scale reads 0. The scale is marked in Roentgens, which is the unit employed in measuring a quantity of ionization. When the indicator is set on 0, the dosimeter is properly charged and ready for use. Another Radiac device used to safeguard personnel is the pocket chamber. Unlike the dosimeter, it has no scale and may not be read directly. Pocket dosimeters and chambers give readings of total amount of radiation exposure, just as the mileage counter registers total distance. But since a harmful amount of radiation can be absorbed very quickly in a heavily contaminated area, it is necessary to have instruments which will give readings of radiation intensities at any particular time. Again, like a speedometer, which gives you the rate of travel. For field survey work, if measuring high intensity of gamma radiations, an ionization chamber survey meter is used. Unlike the pocket devices, this meter charges itself by its own self-contained batteries. Here's another survey meter. This chamber collects the ions produced by gamma radiation, which is the most penetrating kind. But this, a thin window ion chamber, may be used to detect alpha and beta as well as gamma radiation. Gamma rays, which are the most likely to affect personnel because of their high penetrating ability, pass through the case of the instrument with ease. But beta particles cannot enter, and neither can alpha particles, the least penetrating of the 3 kinds of radiation. But when a knob on the chamber is turned, opening a slide on its underside, both beta and gamma are admitted, but not alpha. That's solved by turning a second knob, opening another slide. Now it is possible to read alpha as well as beta and gamma radiations. The proportional counter, which has a greater charging voltage than an ion chamber, will count alpha particles in the presence of a strong beta-gamma background. To appreciate its selectivity, think of an orchestra conductor whose trained ears are attuned to pick out from a mass of music the distinctive sound of a single instrument. Another useful instrument is the Geiger counter. Its sensitivity is achieved by a further increase in charging voltage. In these instruments, ions are speeded up toward the collecting electrode, producing secondary ionization. One initial pair of ions can cause up to 1 billion events, which avalanche toward the electrode. It's like a landslide touched off by a rolling stone, gathering momentum and mass, and ending in a crashing climax. Radiation intensity is registered on the dial of a Geiger counter, and it can also be heard through earphones. Conceive of a hearing aid that would make a tumult out of the movement of a fly on the wall. And you'll get an idea of the amplifying powers of a Geiger counter. These, then, are some of the miraculous members of the Radiac family. But before they're used, they all must be calibrated just as guns are properly sighted prior to firing. Let's watch while this man prepares to calibrate these gamma survey meters. He will have to work in a radioactive area, and even as a doctor protects himself while working with infections, he'll keep a check on himself by means of pocket dosimeters or chambers, and, as in this case, with a film badge, which he'll wear while doing the calibrating. He checks the accuracy of the meter by taking readings at fixed distances from a radioactive source of known intensity, which is a cobalt-60 capsule. The reading is recorded. Then the instrument is moved to the next mark, where the procedure is repeated. Other techniques are used for alpha and beta instruments. Assume an atomic bomb explodes in the region of an important military establishment, like a Marine base. An Air Force base. A naval shipyard. An army camp. Disaster control plans are immediately put into action. In atomic warfare, an urgent problem confronting the commander is to determine whether or not there are any radiological hazards in the area of a bomb explosion. So the monitors go into action. Their job is to get the facts through the prompt and effective use of RADIAC instruments. Except for high air bursts, atomic bomb explosions, particularly surface or subsurface explosions, may leave some ground radioactivity, or radiological warfare agents may be disseminated. The existence and seriousness of these hazards must be determined. Their pocket dosimeters give the monitors the radiation dosage to which they have been exposed. In a suspected area, monitors proceed with caution. They wear protective clothing, check themselves frequently. Each zone is covered thoroughly. Readings are taken and transmitted to a communication center. This information is turned over to a control center, which maintains a continuous estimate of the radiological situation. Hot spots are recorded. These points of contamination are the dangerous rocks and shoals of an area to which an A-bomb has paid its violent visit. The monitors leave nothing uncovered. Specimens are taken for laboratory analysis. Earth, being porous, is susceptible to serious contamination. Samples are carefully prepared for examination. The prepared sample is put into a lead shield containing a counter tube which transmits information to a scaler. This furnishes data for determining the rate of radioactive decay. The alpha activity of the sample is measured by a laboratory proportional counter. There are other techniques for estimating the amount of alpha activity. When you examine under a microscope a special photographic plate that has been exposed to such emissions, you see this. What roughly resembles a culture of bacteria are really tracks made by alpha particles. As these laboratory and field operations continue, monitors themselves must be examined for contamination. They check at decontamination posts and turn in their film badges and pocket meters. If contaminated beyond a usable condition, the monitors consign their disposable outfits to the rag pile for destruction. The men undergo a thorough survey. Then the added precaution of a soap and water treatment. Film badges are recorded development. And pocket chambers are read. Everyone gets the full treatment. But wait a moment. Those clicks in the earphone spell radiation intensity. And when it's a steady crackle like that. Uh-oh. Where you been sitting, Mac? A monitor frequently makes direct contact with contamination, especially when he sits down. And when he does, he loses his pants. But the film badge he turned in isn't lost. It's sent to a photo lab. Radiation takes its own picture, producing blackening of the badge's photographic film. The lead cross admits only gamma radiation. The exposed portion, gamma plus beta. The film is developed and read with a densitometer, which measures the darkening of the film in comparison to a blank, unexposed specimen of the same film stock. The technician files the film away in a rogues gallery of radioactivity as a permanent record. Following the initial emergencies wrought by an atomic bombing comes reconstruction work. The advanced scouts and watchdogs for the repair parties are the monitors. As soon as possible, utilities are restored to operational efficiency. The search for patches of strong radioactivity is exhausting. When found, steps are taken to cover them. Nothing escapes the monitor's attention. Normal living and daily routines are resumed in a bombed area as quickly as monitors can give assurance of safety. They inspect food and provisions for possible contamination. They collect water for laboratory study. Atomic warfare has widened the field of radiation detection, bringing the instruments from the cloistered confines of scientific laboratories into the open. Efforts continue to perfect them for field work, to make them more compact, mobile, and rugged, whether aloft, on land, or at sea.